Bom dia, buenos dias, good morning. This is our second lecture coming from Professor Howard Witter. Thank you for coming. And we are following this School of Advanced Studies in Water and Society Under Change, and I hope you enjoy it very much. Thank you, Howard.
Thank you. Well, this is something quite different from Pat's talk, and it kind of follows the theme that I was trying to develop yesterday when I said we have some major challenges, and to address those challenges we need to organize ourselves a little better, and we need to come together as a community across disciplines, and we need to make some strategic research. And I'm going to give you an example of a program that I conceived and led in the UK a few years ago to try and understand the behavior of river basins that are dominated by groundwater. And so we conceived of a national program which was called LOCAR, Lowland Catchment Research. And the community came together and put a proposal to our major government funding agencies. That was a proposal that was successful for about £10 million. And then the community bid for research to address the challenges that we saw. Let me just see, yeah. So one of the ways we learn about how hydrological systems behave is by studying them in detail. And there's been a tendency, certainly in the UK, but I think generally, that there's been a focus on upland catchments, headwater catchments, the catchments that like hill slope hydrologists have studied for several decades. But actually, most people live in the lowlands, and upland systems tend to be surface water dominated, and many lowland systems have really important roles for groundwater. So the science base is much more limited for groundwater than it is for surface water. So that was really an important motivation for this program. The historical focus in the UK had been on a few sites. Plynlimmon in mid-Wales is a very important one. There'd been other work on forest hydrology in the east of England and in Scotland, but really nothing of any significance that had brought the community together to focus on groundwater challenges. So in the UK, there are two aquifer systems that are important, and one is the Triassic sandstone, which is shown in red, and the other is the chalk. And I'm going to talk exclusively about the chalk. You've maybe heard about the White Cliffs of Dover. If you get a ferry across to the UK from France, you see white. This is the chalk rock. And it is the major aquifer of southeast England. And it's very interesting strategically because in the UK, we have a lot of rain over here, and we have very little rain over here. Here we might have 2.5 to 3 meters of rain a year in Wales. It rains nearly every day. But down in the east, where Pat and I live, maybe the annual precipitation might be 500 millimeters, maybe 600 millimeters. The same as Tel Aviv. And yet the great population density in the UK is London in the southeast. So we've got all the people living where there's the least rain. And so the chalk is a really interesting aquifer. It provides the majority of water resources for several parts of that region, and also it's the major source of flows in the River Thames. So there are lots of pressures on this resource. There's simply pressures of water quantity, and many people don't know this, but you may remember that we had the Olympic Games in 2016 in London, and there was nearly water rationing at the Olympic Games because we were facing a major drought, but actually it rained. These aquifers are very sensitive to winter drought. So the hydrology is really interesting. We have precipitation throughout the year, but in the summer, it's nice and warm, the crops are growing, it evaporates. So the recharge to groundwater is zero. And then we enter into the autumn, and the evaporation reduces, we have precipitation, we start to get recharge. And over the winter, we get recharge of the groundwater, and then the spring, it stops because the plants are using the water again. So what really matters to the water resources is a dry winter. And if we have 2 dry winters, the chalk is really struggling, and that was the situation in 2016. There are also a number of pressures around water quality. So there's a lot of this aquifer. Some of it is confined, but a lot of it is unconfined, and it's subject to agriculture, and so we have major issues of agricultural contamination, nitrogen and phosphorus in particular, and also, of course, some sewage loadings discharging a certain number of nutrients into the streams as well. There are issues of ecological quality, and some of these rivers are very important for salmonid populations, and those populations have been really plunging. So what we wanted to do in LOCAR was to pull together hydrologists and ecologists into an integrated program. And it was really the first time in the UK that we tried to do this on a large scale, and it was very hard work, but ultimately quite successful. So the main thing is we really wanted to understand the interactions between the surface water and the groundwater and the water quality and the ecosystems around these chalk rivers. They're quite special habitats. And then secondly, we wanted to improve modeling tools so that we could represent these processes better for water management. And just to give you a story, I mean, Thames Water is now a privatized company that runs water resources in the Thames region, and they have a water resources management model which is quite sophisticated in terms of surface water, but it's totally primitive in terms of groundwater. It's really inadequate in its ability to simulate groundwater drought or groundwater flooding. Oops. So, yes. Okay, so what we did was to instrument these basins in a number of ways. So clearly, recharge is really important, and so we developed recharge sites. So this was at a time when eddy flux techniques were relatively new, so we could measure directly actual evaporation for the first time. We had arrays in the ground of neutron probe access tubes, so we could measure vertical profiles of soil moisture. And we had tensiometers to look at the pressure dynamics in the near surface. So quite comprehensive sites for looking at evaporation. We drilled a lot of wells, and you can see a drilling rig down in the valley floor here on the floodplain, and a well completion. And all the white here is the rock that's been brought to the surface. The chalk is a white fractured porous rock. We had a lot of sites in place for measuring water quantity, and those were augmented to measure water quality. We did some really exciting things on the ecological side. We tagged fish and observed diurnal fish dynamics in some of the streams and so on. Lots of fun. So we had this money to spend, and we then invited bids for projects, and it was quite interesting. And if any of you have been involved in interdisciplinary projects, this might resonate. But we had some really good hydrologists putting proposals together with really weak ecologists, and those proposals failed. And then we had really strong ecologists working with really weak hydrologists putting proposals together, and they failed. So we had to do quite a lot of work to build strength in the community and to put together teams that could meet some of the objectives that we wanted. And here are some of the projects that were funded. We were looking at improved methods of evaporation, influence of woodlands on recharge, looking at the mechanisms of flow in the unsaturated zone, but also the transport of nutrients, trying to understand groundwater flow using tracers, groundwater studies using detailed borehole arrays and stochastic modeling, assessing stream aquifer interactions using a range of hydrogeophysical techniques, looking at recharge through the quaternary drift deposits in these regions, a whole series of projects looking at sediments in the rivers, vegetation, growth. These streams are quite slow moving and they suffer huge growth of sediments, huge growth of vegetation in the summer, which restricts the flow. How should these be managed, and so on. There was a major project which I led on nutrient management, and as I also mentioned, various fishery studies to do with fish dynamics and fish populations. We included a major freshwater fishery research site where they had experimental flumes that they could look at population controls and population dynamics. And looking at the significance of exchanges between surface water and subsurface water. So a whole range of quite interesting programs. I'm just going to talk about some of the lessons based on the chalk catchments that I was particularly involved with, the Pang and the Lambourne. These are tributaries of the Thames. And there's some interesting lessons. Even if you're not really interested in groundwater, there's some interesting lessons here that I'll try and bring out. So this is what the chalk looks like. And it's quite complicated. So it's all made of seashells, but it's a highly porous medium, but it's very strongly fractured, as you can see here. So both in the unsaturated zone and the saturated zone, these properties of a porous medium, which is highly fractured, are really important. And I think I try and convince my hill slope colleagues that this fractured porous media occur everywhere. And what's really interesting about the chalk is it gives some insights that I think we can use in many other situations. So this is an example of the topography of the two basins that I'm going to talk about. So here we've got the Lambourne, and here we've got a stream called the Pang, and they're both tributaries of the Thames. The geology of these systems is quite interesting, because the Lambourne is almost entirely a chalk-covered basin, and the Pang is chalk in the upper reaches, but it's got these tertiary deposits down at the bottom. So bear that in mind when we look at the hydrology. So this is a typical chalk stream hydrograph. So it's totally seasonal. You see the annual cycle. We have the winter recharge leading to a rise in the spring flows and then a decline. And when it rains, we get these little wiggles because it's raining on localized areas that are relatively impermeable. So that's what a chalk stream looks like. Now the Pang has got this strong chalk area, but it's also got these tertiary deposits. So when it rains, we've got the underlying groundwater response, and then we have these really sharp peaks. So looking at a hydrograph tells a story about how a catchment is behaving. And if we look at the chemistry, then we can see that the Lambourne, the chalk catchment in blue, is very tightly grouped on this chemical diagram, this Piper diagram. But if we look at the chemistry of the Pang, then the tertiary deposits spread way out in the green. And so when we look at the water in the streams, it's a mix of the pure chalk water and the water from these tertiary deposits. So there's a clear chemical signal here also as to how this basin is behaving. Now, this is a diagram which shows groundwater contours, and it shows them at different times of the year. So there's the autumn of 2002 and the spring of 2003. And if you look very carefully, you can see there are some changes to the patterns of the groundwater contours. And these red lines that are drawn are to show the boundaries of the groundwater that's contributing to the Lambourne and to the Pang. And what you can see is that they move, okay? So the dividing line between the catchments is here in the spring, and it's here in the autumn. So lesson number one, we don't have a fixed catchment area, okay? This is a huge challenge for any hydrological model. No hydrological model that I know of can handle this. So beware of groundwater catchments, because basic problems arise, like not knowing the catchment area, it's dynamic. So talk a little bit about the geology and the hydrogeology of the groundwater system, first of all. So I'm going to take you to some groundwater at a place called Trumpets Farm. Funnily enough, our students from Imperial College still go there every year and do pump tests. So one of the advantages of having these experimental facilities is that they are immensely useful for decades afterwards. So this was a set of boreholes that were partly based around a well that had been developed by the Environment Agency. And so we got various boreholes put in with piezometers to different depths and casings at different depths. And a whole series of studies were done to monitor the groundwater in the natural situation and then to pump the well down here and observe the changes. And a lot of work was done to look at the properties of the boreholes. And so this is a measure of the hydraulic conductivity, pretty low at depth, increasing as we move up, but really very variable in samples taken at different times of the year. And if you look at the logs from the boreholes, then you can see that some very highly permeable sections, 60 meters a day, hydraulic conductivity pretty high, and strong presence of these large pores or intersecting fractures, but others, segments of the same borehole, really a very low conductivity. So quite a lot of work was done to look at the geophysics using gamma logs, caliper logs to measure the width of the borehole, looking at the temperature of the water in the borehole, and looking at flow changes. So one of the things that you pick up here is that there are some distinct changes in the temperature profile, and that means that there are changes in the water flow into and out of the borehole. Okay, so inflections in temperature are indicating flow horizons. And here we've got a steep vertical gradient, which means in temperature, which means that we have rather low flow in that section. And there are some complexities in the data with slightly different stories from different measurements. But the basic story is that we're seeing water coming into the profile from the base, from lower down. We're seeing some water lost at this horizon. We're seeing quite a lot of water gained at this horizon and water lost at those horizons. So it's a complicated story, and simply by putting a borehole here, we are interconnecting these fractures, which would not normally connect. So just by putting a borehole in, we're actually changing the flows. And some very high flow rates within the borehole. Okay, now the same story when we pump the well nearby and observe the response. So the same kind of data, and we've got temperature changes in the profile and so on. But now, if we're looking at the flows, they're completely different. We've still got this upflow at the base. We're losing a meter cube per hour here. We're gaining 0.84 here. We're gaining 2.4 here. We're losing 1.2 there. That's quite a different pattern to the one that we saw from the unpumped situation. So, there's a very basic message here that if you were putting a well into a fractured medium, first of all, just by putting the well, you're interconnecting various fracture systems. And secondly, if you start to pump that well, then you trigger flows in some of the fractures. So you're actually generating a flow field that would not naturally occur. So this is important because most hydrogeologists use wells and they pump wells to determine the aquifer properties. But in a chalk system, that's really unreliable. Okay, so you have to take any data from these wells in terms of aquifer transmissivities with a very, very large amount of uncertainty. And they don't really work. That's one important lesson from this. Stream aquifer interactions. So really, it's very important in terms of the stream to understand how the groundwater is contributing. And we can't tell too much from our wells, as we just discussed, they're flawed, but what we can do is look at the profile of flow in the stream and see how it changes as we move. So as we move downstream, we get a progressive increase in flow, but there are various nick points that take place. And if you look at the variability in time, you can see that the flows increase and decrease, but there are certain points here where there are major inflows, and there are also certain points where there are losses. So we've got some very important spring systems feeding water in at certain locations, and we've also got losing reaches where the river itself is contributing to groundwater. And the whole geology is pretty complex because there are a number of faults, but you can see that we've mapped some major spring sources on the systems in blue, and some areas where maybe the faults are also controlling the fractures and the hydrology. This is quite a complicated system with a lot of natural sinkholes. So the chalk can be eroded by flows, and so you can be walking through a forest and you'll see a sinkhole, often from a legacy climatic environment. And so these are very extensive over the region, as you can see, and also extensive springs. So it's a very complicated area. But the upshot really is that the stream is the signature of the groundwater, and we have a lot to learn from the stream about the groundwater dynamics, and we have a lot to learn from the stream about where the groundwater is interacting with spring sources and also where it's losing. So one of the things that we did was to put in borehole arrays adjacent to the stream. So the main channel, so we could kind of understand these spring flows. So we have a lot of data from these, and these graphs are a little bit complicated, but they show the river upstream and the river downstream and the river at the site of observation. And some of the wells in the center of this reach reflect quite closely the upstream river levels, and some represent the downstream river levels. So there's a complicated set of interconnections, even within wells that are located just a few meters apart. And so we built up a picture of this system where we've got this highly the chalk providing water into a zone underneath the river which was highly fractured, and then within the river we've got the river moving water, but we've also got the area underneath the river moving water with different kinds of connectivity determined by lenses between the groundwater and the river water levels. So it's quite a complicated story that's emerging, and that of course feeds the ecology of the river. Now, the recharge is really important. So the recharge is the water resource, and the recharge is also how contaminants get into the groundwater. And the unsaturated zones vary in depth. They can be 10 or 20 meters, they can be 50 or 80 meters deep. So trying to understand how water moves through the unsaturated zone is really important. And for a long time before this study, there was a real puzzle as to what was happening in the chalk, because part of the response was really quite dynamic. So here we've got a diagram in which we've got red is effective precipitation. So we've got rainfall, less evaporation. So this is pulsed over the winter months. And what you can see is that we get a pulse of effective precipitation and then quite a rapid response in groundwater level. The precipitation ceases in the spring and the groundwater declines. Okay? So that's the story that I was telling you about recharge. So that's kind of simple, straightforward, and you can see it's a very rapidly responding system. Now, on the other hand, if we look at solutes in this system, and this is a profile of nitrate from the ground level to 40 meters below the surface, and these are data that are 3 years apart, then you can see that the nitrate profile is moving down by 2 meters in 3 years. So we've got this real puzzle that the water table is responding very rapidly, and yet the solutes in the chalk are moving down maybe at a meter a year. And that puzzled people for a long time. And the answer, of course, is that we've got this complicated fractured porous medium. And when we get these intense episodes of net rainfall at the surface, they're capable of moving down through the fractures. But the nitrate, the solutes, are moving down, they're diffusing into the matrix, and then they're moving down very slowly. So it's a really interesting and important part of the behavior. So if you have 40 meters of unsaturated zone and you have nitrate moving down at a meter a year, how long does it take for the nitrate to move down? 40 years. So this is a huge issue in terms of what we see in terms of nutrients in the river system. And if we initiate policy changes to change agriculture, we're not going to see much happening for tens of years. So that's an important story for policy and management. So we've got those arrays that I showed you earlier, and they gave us some really interesting insights into some of these processes. And so here we've got a story of groundwater recharge. So here's our rainfall patterns. Here we've got the mafic potential, the suction in the chalk unsaturated zone. So these are all negative. So it's unsaturated. These are negative pressures. The water is held by tension. And you can see that near the surface, we've got a dynamic response, but at greater depth, 4 meters, then there's a slow and much more damped response. And we can look at the hydraulic gradients. So the hydraulic gradients determine the direction of flow. It's negative. It's a vertical downwards gradient for recharge and a vertical upwards gradient for evaporation. If we put that information together, we can see periods where the chalk is near saturation. And at that point, that's what's indicated here. So the suctions are very low, the chalk is near saturation, it's transmitting water through the fractures, and this is the water table response. Okay, so we've got all this precipitation, this is all unsaturated, nothing is happening down here. Suddenly, we're getting conditions near to saturation in the unsaturated zone, we're triggering fissure flow, and the water table is rising. So this is an interesting sequence which we're going to look at. So this is, again, the net rainfall minus actual evaporation. That's what's coming in at the top of the profile, and this is the water table response. So we look at this period, we can see that the recharge is starting to rise here, and the water table is starting to rise here. That's a lag of 124 days, which is 4 months. We're seeing the peak of the recharge here, the peak of the water table rise here. That's a period of 103 days, that's 3 months. We've now got a period of very much more significant recharge, and the response is now 72 days and 22 days. And here we've got a really intense event, and the water table rise is instantaneous. So it's a really interesting and complicated system. So on the one hand, we've got 3 months delay from the surface to the groundwater, and here it's responding in a matter of hours. It's a very interesting story, and I think it applies to lots of hydrological systems. We have this complexity of flows through fissures, which are triggered when we get conditions near saturation. And then the rest of the time, we've got this very slow matrix response. And understanding this is critical in terms of policy. So we've done some modeling of this, and I don't want to talk about it in detail, but if we model the two continuums and their interactions, we can reproduce this kind of a dynamic. Okay, so one of the major challenges in the UK is to understand and manage nutrients. It's the biggest pollution source. There's been a huge amount of work done on agricultural policy. What they do is interesting. We've got data from measured river flows, and where we don't have data, we've got some simulated river flow quality data. And if nitrates or phosphates are above limit values, then a restriction is placed on all farmers upstream of that measurement point. So they can use fertilizers, but to a limited extent, and it's controlled how they can apply the fertilizer. So it's a very big deal. How do we understand what's happening in these systems? Well, there's a model that some of you if you work in this area, will have heard of. It's called INCA. It's a nitrate model developed by a colleague called Paul Whitehead, who was at the time at the University of Reading in the UK. And it's like many of these models. It's a simple hydrology model with a couple of boxes. It's got a soil zone, and it's got a groundwater zone. And it represents in a simple way, the rather complex processes of the nitrogen cycle. So it's got nitrate addition from fertilizers, plant uptake. It's got denitrification and nitrification and mineralization processes. It monitors nitrate and ammonium species. And it represents leachate to the river and to groundwater. Problem is, it doesn't have a deep unsaturated zone. It doesn't have a memory of decades. So one of the things we did was to develop a chalk version of that, where now we had a probability distribution of travel times that would allow us to get the long-term response of nutrients traveling down to the chalk. This was developed by somebody called Beth Jackson, who some of you might know. She's currently an academic in New Zealand. So here we've got the topography of the Lambourne catchment. We know the groundwater elevations, so we know the depths to the unsaturated zone. They look like this as a distribution. So they range from 0 to 120 meters depth. And we can associate travel times with that, and then we can build that into our model. And then we can look at very long sequences. So here's a sequence of observed flow and simulated flow in the Lambourne catchment. So here's our period of observations in black. And then we've used the historical data to simulate back to 1920. And we've looked at projections forward for to the end of what's the date here? To 1998. So here is our simulated nitrate, and here are our observations. And if any of you have had experience of modeling nitrates, you'll know that although these results don't look great, they are great. And then what we can do is put climate simulations and policy decisions onto this. Okay, so what we've got is different areas of agricultural activity. We've got grassland in red, cereals. We've got a set-aside policy. We've got, I can't read what that is actually. Anyway, let's go with the grassland and the cereals. And then we can look at different policy, at different policy options. And we're running now from the 1930s to 2091. And what we're doing is cutting the nitrate loading to 0 in 2003, which is when the work was done. Okay, so we're cutting down the nitrate inputs. And in our cereals, we've got increasing nitrates leached from those cereals up until the 2050s. With the grassland, it peaks a little bit earlier in the 2020s, and then we've got a decline. But the important message is that we've got several decades of lag in this system. And all around the world, there's a major policy dilemma because people are recognizing the impact of nutrients on aquatic systems and drinking water, for that matter, because there are many parts of the world where nitrate levels exceed drinking water. And people are looking to agricultural policy, and they've been implementing it now for maybe 10 or 20 years, but they're still not really seeing major results. And partly that's because of the policy not always being well implemented, but partly people are not recognizing these really large lags. So we've got this legacy of decades of contamination. And some interesting work's been done by a former student of mine, Nicholas Howden, who's now at Bristol University, looking at really long records in the Thames for 100 and 200 years of nutrient loading. And you can see the Industrial Revolution and the Agricultural Revolution. You can also see when we had the Second World War and Britain was very short of food, and so a lot of agricultural land was ploughed and planted, and that released nutrients. And we see that pulse 40, 50 years later coming through in river flows. So, a little bit about LOCAR. It was the first time that the British community as a whole had come together to work on a groundwater problem. We had a load of universities working with this. We had Keith Bevan and other colleagues from Lancaster, Imperial, where I was, were a leading force in this. Des Walling and people from Exeter on the sediment side. The Centre for Ecology and Hydrology did some great work on various aspects, and the British Geological Survey. We all came together, built a big, strong team, and got a lot of insight. And the funding, of course, ran out after 5 years, but the installations remain, and a lot more has been learnt from them. Certainly, it's a story where we really need to understand these systems and their complexity to really make sense of management options. There's some particular messages. Be careful when you're drilling wells in fractured porous media, because you can't always believe the results that you get from them. And also the unsaturated zone, which so many people neglect, is just so important and complicated in the transmission of water flow and the movement of nutrients. Now, this is still really to translate properly into large-scale groundwater models, and it's still an objective of the British Geological Survey to try and get together a decent groundwater model of the Thames that reproduces these processes and can then be used to help guide water management policy. There's big arguments about water resource developments in the Thames region around groundwater and the future of groundwater. But groundwater projections, so I mean the tensions are interesting because we have very big leakage in London, but on the, and so there are people that want to build a new reservoir near Oxford, and the regulator is saying, well, you can't do that unless you solve some of the leakage problems. Anyway, we need models, and we need improved models to be able to move forward with serious projections. The UK currently is vulnerable to 2-year droughts, and that vulnerability is likely to increase. We've got increasing population growth in the region, and the signals of climate change are hotter and drier summers. Possibly wetter winters, but there's a question as whether the drier summer means that the recharge in the winter will be less or not. So it's quite likely that climate change will further stress these systems, but people already are stressing these systems. And I present it to you as an example where if we have a major problem in managing an important resource, we can't do a lot as this individual researcher, but if we can gang together, persuade our funders that there's a serious problem and we can make progress, then we can get together and do great things. Thank you very much. There's a special issue of Journal of Hydrology on the LOCAR and loads of papers.
Thank you, Howard, for your presentation. Coming from physical hydrology, coming into more important anthropogenic effects, especially in some parts you mentioned the lack effect we have in nutrients after decades. And perhaps I brainstormed in my mind about some Anthropocenes, small signals we have still in the last 1 or 2 centuries. Also in South America, there's a neotropics lands, but also we had a very high signals from anthropogenic
Yes.
effects.
Well, I wondered how many parallels you saw from this to your situation here in Sao Carlos. So,
yes.
I think
So I have well, we have time. I have a question, but I need 4 volunteers to co-author my questions. I'm still warming up my question, but I need 4 volunteers to pick up the model and bring the model here. The model that's outside.
yeah.
We can put here, we can explain better the question in a practical way. So 1 volunteer, 2, okay, please. So I'm warming up my question. The question is, it's very interesting that it is fractured chalk in the experimental site. Well, we have now this kind of soils in the neighborhood here, but of course, please, go ahead, put here. We got a mixed approach from our confined and unconfined aquifer. So the aquifer is the blue part here. Here is the outcrop, and that's the surface, the ground surface. So people are living here, and we have 10 kilometers times 10 kilometers. This is São Carlos. And we have also here people in all these parts living there. It's about 230,000 inhabitants, pumping and using this water, sometimes very in the surface and sometimes very confined. And the first question, that's what Professor Edson mentioned yesterday, that from the Guarani aquifer, as only a small part of the aquifer is emerging at the surface. But through this emergence frontier, we have cities. Okay, no problem. That's okay. Obrigado, viu? The point is when mostly when this aquifer is emerging, there are cities in the frontier. And the point is, in some part, they are pumping, and no idea about this water pumped is emerging in other parts. So the first point is about, this is for both. One is the idea from physical aspect, and the other from the governance, because it's a transboundary effect, you know? So you have in a small neighborhood here, we have a governance problem, because people are using water from the same aquifer, but with different value in terms of extracting water. The water withdrawal value and cost is different. So, 2 questions. The first question is to you, Howard. How can we, coming from physical hydrology and knowing better these problems of aspects of dynamics, the flexibility of the frontier of our system you presented, the boundary of the catchment is moving through the seasons. So we are a dynamic approach about the aquifer here. How can we, experimental physical hydrologists, can we better explain for governance people to achieve better governance models about the wise water use we are thinking for? This is my first question for you.
Well, I've had a lot of experience in talking to people, even judges at the International Court of Justice, about groundwater. And a lot of people get it, but a lot of people simply don't understand groundwater. I did a case between Slovakia and Hungary, and it was partly to do with the Danube feeding groundwater into the Danubian wetlands and sub-irrigating agriculture and maintaining wetland ecosystems. And I think after many rounds of written pleading, there was still 1 or 2 judges who really didn't understand what groundwater, and they think of kind of underground rivers and so on. So there's a huge issue in trying to explain this, and I think a lot can be done by simple visual communication. So your model would be one example. What we did in the case of the Gabčíkovo case was we made a movie. And we sort of explained how the water was moving in a movie that could be easily understood by a lay person. So I think some really good visualization, and that's an excellent start. And then you can have a water sim 21 to represent the groundwater system, and you can have people putting in contaminants and seeing where they move and looking at the timescales. So a nice little groundwater model underneath there with some nice visualization. And I think you could start to have a really interesting dialogue about the management challenges. But you've got to have the processes in there correctly represented. So I think you've got some real opportunity to do some great science, and I know you're starting to do that. I mean, we've got terrific tools now, and I know you're working with isotopes and other, so we can look at groundwater signatures. We need much better information on how much water is being withdrawn from groundwater, and we need good quality monitoring sites. But once and that includes monitoring the precipitation and the actual evaporation. And then we can put the story together and in a way that is going to be relatively simple. And then we can run scenarios, and I think that's the way forward. Yeah. I mean, I'll tell you, it's an interesting story about London. So the Chalk is the major water supply for the southeast, and London is a classic confined basin. So we have the London clay, which forms a bowl over the Chalk, and right in the centre of that was Trafalgar Square. And any of you who've been to London, there's Trafalgar Square, there's some fountains. So traditionally, those would have flown naturally from artesian pressure. But then we had the Industrial Revolution. And so people drilled wells for public supply, but also a lot of wells for industrial use. And so the water table, instead of being at the surface, went down 100 meters and stayed there because people were using all this water and polluting it. And then they stopped using so much water because there was no more big industry in central London, and there were other sources of public supply. So guess what? The water table was coming up a metre a year. But now what we have in London is underground stations, very tall buildings with very deep basements, and suddenly all these were being threatened because of rising groundwater levels, natural recovery from the situation 100 years ago. And there was a real governance problem because nobody owned that problem. Whose responsibility was it? Anyway, in the end, there was happy ending because the various interest groups came together and they now pay for a groundwater management scheme, so they're essentially pumping to keep the levels artificially low so that the infrastructure can remain intact. And that's not a story that's unique to London. I worked in Riyadh quite a bit in the 80s and the 90s, and they had the same issue, that they piped a lot of desalinized water into a desert city, Riyadh, and they had imperfect storage with lots of leaks, and then they didn't really have proper sanitation collection, and so suddenly the wadis in central Riyadh, instead of being dry for 99% of the time, were perennial flows, and the basin and the tall buildings were in danger of falling down, so they were only kept standing because people put wells in the basements to draw down the groundwater. So some interesting historical wrinkles on this story.
Urban landscape are still exciting us about hydrology, governance,
Yes.
source,
Yes.
and decision making. That's
I think there's the huge challenges and opportunities to better understand groundwater in urban areas. And some decades ago, there's a guy called David Lerner trying to develop an initiative in this area, but still I think there's relatively little known and relatively few well-instrumented case studies.
Well, thank you. And the second is taking a vision about 100 years ahead. So to become climate resilient or water resilient, we need to have visions ahead, several decades. São Carlos, for instance, is making a challenge about 100 years ahead. So in your opinions about Phoenix, London, and some Brazilian cities, what are the pros and cons in terms of taking decisions under uncertainty, but having a very heavy knowledge about physical hydrology we have in Phoenix, in London, in the neighborhoods, in the United Kingdom, also in Brazil. So, in your opinion, what are the main reasons we can overpass in the next decades, perhaps, and making for the early career scientists to achieve these long-term visions?
Okay, London has two major challenges. One is droughts and water supply, and the other is flooding. One of the things it's done already as a contingency for drought management is to build a desalination plant. So it's not routinely used, but it's there as contingency if needed. So there's some infrastructure in place that could be used. Flooding is really interesting. The whole of the east coast of England is low-lying, and in 1953, a lot of it went underwater. We have high tides, and then we can get storm systems moving down the North Sea from north to south, giving us a tidal surge. And in 1953, there was a major tidal surge, and hundreds of people lost their lives, very large areas went underwater. We have flood defences, but they're still vulnerable. And there's a major challenge to how to manage that kind of coastline, which is geomorphologically quite dynamic in the face of rising sea levels. The London solution, like the Dutch solution, is to keep it out. So we built the Thames Barrier, and had it not been for the Thames Barrier, London would have been underwater several times. So the Thames Barrier recognises a threat, and then it simply brings up gates which normally sit on the bed. They allow ship movement, but they stop the ships, bring up the barriers, keep the sea out. At the same time, of course, the River Thames is still flowing, so they can't keep them. They have to open them on the tidal cycle to let the fresh water out. We will need a bigger Thames Barrier in coming decades because of sea level rise, but it's been a really successful intervention, rather unlike the Venice Barrier. So that's one solution. Yeah. And of course the Dutch mostly live below sea level, and they have lived with this challenge for centuries. And their solution is to build big dikes and keep it out. But that raised challenges for society and for ecosystems. Yeah.
I'm going to take my time to tell you a very bad story. And I don't know if it has a happy ending, to offer some insight into I think the issue that you're bringing up is an issue that we've faced since Phoenix began to grow quickly, and that is the potential for certain users of the aquifer to impose costs on neighboring communities by the nature of their use and the consumption of this resource. So you can have some transfer of risk going on with the use of a watershed in a complex place like a city. And so here's the story. Seeing this potential problem, which was clearly an issue for us, and I hope you recall the map that I showed you of all the different users of the aquifer, the fragmented governance system that exists above ground. And the story is about how it manifests itself in the water use and imposes costs on we're transferring risk to other places by the way the aquifer is used. So seeing this was seeing the problem of an overused, unsustainable aquifer. In 1980, the legislature for the state of Arizona passed a innovative Groundwater Management Act. And what the Groundwater Management Act did was to place limits on the pumping of groundwater to achieve sustainability. We need sustainability because we want to continue to use that resource as the bank. That's the bank that sustains us over the long term. So this was a very, the governor of the state at the time was an environmentalist, and he twisted arms and cajoled the state legislature and the public to support this management of the aquifers that sit under many of the, some agricultural regions and sit under, there were 6 what they called active management areas where we're going to be particularly concerned with aquifer management. We're going to monitor what's there, and we're going to manage successfully the use sustainably, the use of those 6 aquifers. So the farmers buy into this, the cities buy into this, the Native American communities who control much of the water, or a significant chunk of that water, buy into this solution. And one important, one of the signature aspects of this system was that communities who wish to pump groundwater need to demonstrate, or a developer who wants to build housing units in any of these active management areas, in the active management area that sits above Phoenix, must demonstrate that he or she has a 100-year supply of water to be able to proceed with their new housing development. So you need to show that you have secured water rights from the Native American communities. You've purchased water rights from other communities, that you can demonstrate that you have 100 years of sustainable water to support any kind of urban development, any new housing construction. So everybody people thought this was a good idea, and this is the way we will proceed to protect this valuable bank that we have of groundwater. So this went along for 10 years, and the developers were unhappy. Remember what is the signature for Phoenix as a city? What is the basis for the economy? It's new home construction and growth. So this is a place of the future, a place of growth. Well, this requirement for a 100-year supply started to get in the way of developers. And the developers' capacity to build new homes. And so the state legislature said, the politicians said, well, maybe we're going to create a groundwater, we're going to allow cities to, we're going to create what's called a groundwater replenishment district. And this is about the time that Arizona started to receive large water via the Central Arizona Project to Phoenix. So we're going to get Colorado River water into Phoenix. And the idea was that we can use that Colorado River water to help the developers to be able to to be able to realize the American dream and to be able to stipulate that they have an 100-year sustainable supply. So this is this is passed by the state legislature. It essentially undermined the principle that was first established in this Groundwater Management Act. So, but for some years, for a few years, it did work as we received part of Arizona's allotment of Colorado River water. Now that half of that water has been, I think I mentioned yesterday, has been allocated to the Native American communities, and so thus they become the decision makers in how this water is allocated. They're supporting growth and allowing their water to be used for to meet the needs for the 100-year supply. And we've got this complicated urban pattern that you alluded to a bit with, well, what happens when people in this community use water to a neighboring community? So we've got all of these communities that are almost totally dependent on groundwater to support urban growth at the urban fringe. And they have been granted by lawmakers and political leaders of the right. What happens then, and what's part of the public conversation now, is that your growth out on the west side is compromising our long-term sustainability. We have enough water to support urban growth in our region, but your use of water is unsustainable, and you're imposing costs on our long-term development at adjacent communities or communities on the east side. And so the answer is political. The answer is that this is we have taken a sustainable water act and it's resulted in an unsustainable long-term use, and that fragmented network of governance impedes the sane and visionary and safe management of this groundwater base. So we're waiting. I mean, this is a issue that crops up every couple of years. The politicians don't have the political will to enforce a program that's on the books that would sustain this resource. So the answer is, the answers are two. I mean, the first answer is we've got to govern water resources in this region as one region. This crazy patchwork of 120 water providers, each competing for the same resource, and any lack of a sharing plan moving forward is a great loss of opportunity for this region. But I'd say if there's any lesson learned, it's we've got to convince the public that this is that these problems are going, the ones you just described, are going to be rampant unless we find some way to manage this resource as a single urban region rather than as fragmented pieces. That's my message.
Thank you, thank you. And also we have uncertainties and we have a certain situation. Here, look at here. This is the future. The future is here. You have people coming native from 11 Brazilian states, also from other countries here, from Colombia, myself from Argentina. So this is this sureness that is we are putting also the discussion into education. An education vector driver, sorry, is one important point to shape the future. So if we maintain this alliance with examples with Saskatoon, Phoenix, London neighborhoods, São Carlos or São Paulo, we can produce some comparative lessons learned and experiences gained from each other. And we, at this moment, especially in Brazil, we are discussing this new paradigm in between having water management from the supply, that is more traditional, towards water management from the demand side. And that is we are in the turning point. And here we are depending from the discussion of the future. So I am very, very happy, not only from the lectures, also from the discussion about the visions we can share with these young people at the short term, because they are making their Master of Science, PhD postdocs here, and also people from the undergraduate. We have undergraduate here, in this room. So I thank you very much. Thank you very much for your comments. Of course, this is open for new inputs, and I would like to invite Felipe to come here to explain what about the next steps about today and the next days, because tomorrow we have also more discussion about coming from the students. Tomorrow we have four tournaments, four plays here being chaired by the students. Okay?
So, should I say? Okay, let's speak in English. So this afternoon we have no lectures. We will continue on Thursday morning, right? The people who are watching us on YouTube, tomorrow we don't have lectures online, so you are free. But people who are in São Carlos, tomorrow we have the workshops with the students. These workshops are present by some students who are here: Cesar, Bruno, Gabriela, and me. Who will be here? Yes, and these presentations are part of the qualifying exams of these students, but you are all invited to attend these exams. We will start tomorrow at 8 a.m. 8:30 with Gabriela. The title of her work is Insurance Fund as an Adaptation Measure for Increasing Water Security in Bases Under Change. Her committee is Professor Mário, Professor Diego Guzmán from Colombia, and Professor Shiminkai from University of Illinois. Then we have at 10:30 Ailton Cesar presentation. It will be on Citizen Observatory for Flood Insurance Optimization under climate change scenarios. Then, your committee is Professor Howard Witter, right? And Professor Diego Guzmán from Colombia, right? And then Mário, after lunch, we will start again at 2 p.m. with Bruno. The title of his work is Participatory Study for Best Management Practices, Application in Rural Basins. His committee is Professor Mário, Professor Howard, and Professor Elmira from Carleton University.
This is from Polytechnique Montreal.
Polytechnique Montreal, sorry, yes. Yes. And then the last presentation is my presentation, right? My committee is Professor Patricia Gober, Professor Mário, and Professor Shiminkai. The title of my presentation is Assessment on the Water Supply System of São Paulo Metropolitan Area through Socio-Hydrological Modeling. It starts at 4 p.m., okay? And then we will be back with the YouTube streaming at 8:30 on Thursday, all right? And then we have the last presentations from Professor Patricia and Professor Howard.
They are open qualified. Some more people can here can assist your presentations tomorrow.
Yes, you're all invited to be here.
They are not
It's-
private.
It's open for everyone, so you can come and attend the presentations. Yes, yeah, that's true. The presentations tomorrow will not be here. It will be in our department theater. I don't know if you all know what it is, but I can be here in the morning at 8 a.m., okay, because I have to be there at 8:30. So if you are coming, please be here at 8, then I can come with you to our department and I show what it is.
Whoever likes to follow some of the examinations tomorrow, we can offer an Skype channel or something like that. We have not so many connections, but depending who is going to join, it is possible to have 1 or 2 connections, not an streaming, that as today. That's the point. Okay? We are not open for okay. So we are very enjoyed about these 2 days. Thank you for your sharing pictures and experience. We hope you are enjoying very much, que vocês estejam desfrutando. Tomorrow, this is still an education moment. And it's very important that's how students are working and how the professors are responding to their work. And that is the way we are making education. It's a feedback, a two-way channel process. And this is very important. And it's, of course, a celebration moment because it's a moment of learning to all of us. So thank you for following, and we hope you enjoy very much São Carlos and your staying here. Thank you. Thank you.